This is a demonstration of what to do for the glass microspheres lab, which is the last lab of MSc 3055, the junior level lab, so material processing. Glass microspheres are essentially this stuff, which is perfect sand, right? It's like little balls of sand. So these spheres come from pottery industries. This one in this container is smaller spheres, so you'll see they kind of flow a little bit differently than the others. So you can have the students hold them in their hand. With the large ones like these, you can almost see individual grains by themselves. If you zoom in, you can kind of see like individual particles. These are about 150 microns each. But you'll notice they also clump together a little bit. So to prepare the spheres to be sintered, we're going to make sure that they're not clumped together. And typically what we'll do is take one of these sieves. There's a whole box of various grades. And this is the way industry will make sure that the sizes of these spheres are between two limits. Right? So they'll pour a master batch into one sieve. Everything that passes through is smaller than this size. Then they'll take a sieve. The next sieve down is 140 microns. So they'll pass all of that through the next sieve. And then whatever is between those two sieves, whatever's retained in the second one will be larger than, say, 140, but smaller than 170. So then they can get a sizing right there. So to use this, you would just pour some of these large spheres into the sieve. You can kind of shake it around. Sometimes you could use a little brush and sort of push them through. You don't want to poke the mesh because you don't want to damage any of the holes in there. But that's a very tedious process, and this has already been done. So we really don't need to do the sieve process. It's just kind of a demonstration tool. Okay, so we'll have containers of the large spheres, the small spheres, and one of these dishes will be a mixture, a 50-50 weight % ratio. So we put it on the scale, zero it out, take some amount of these large spheres. You can just put an excess of what you think the students will use. So this we can put maybe I don't know, 50 grams or so. We'll just, let's see what we'll do, 20. Okay, so let's say 21 grams of that. You want to make sure that they're not clumped together, so you can kind of push them down. And then we put the same amount of the small spheres into that and mix it together very well. Once you have those batches, you're going to have each group make one, have one of these graphite molds. We use graphite so that when the glass melts, it doesn't stick to the interior surfaces. Pretty much every other material the glass would stick to. In this lab, we're measuring how much this pellet densifies with the heat treatment process. We bring it to 725C and heat it for either 5, 10, or 15 minutes. You could go a little bit longer depending on how stable it is. So what we need to do, first thing, is measure the size of this cavity. So we use the back side of these calipers, and we use the top numbers here, which are in millimeters, and then these will be, on the red dial here, will be tenths of a millimeter. So this is going to be 12.625 millimeters in diameter. And then for the depth, we're going to use the little periscoping side of this caliper. So go from the edge, you can put it on the desk actually, it's easy. Go to the bottom, and this is going to be 7.44 roughly millimeters. So convert that to centimeters and get the volume pi r squared h in centimeters cubed. After the heat treatment, we'll weigh these pellets, and we will get the final dimensions and also the weight. So we don't have to weigh anything while we're doing this process, but afterward we'll say this number of grams went from this volume to this volume. And when we divide the mass by the volume, those percent densities will have changed. So we'll get some density that's a kind of a large number, maybe like, I don't know. Anyway, we'll get some number for density, but we actually want density as a percentage because we want to know what the porosity of that pellet is. So we have to divide that number by the density of this material itself, which is soda lime glass. And that soda lime glass density is 2.5 grams per centimeter cubed. So whatever density you get, divide by 2.5, and that will be some percentage of density. And what should happen is, if we zoom in on this, we have a chart of the sort of percent density, is that the right way, versus the time, over time. As we, heat these things up, they're gonna start from maybe like 50% dense, and say like this is 100% dense. When you loose pour anything into a mold, even if you pack it tight, it's only going to be about 50 to 60% dense. It's not, even though these are spheres, they're not going to close pack like when we learn in the intro class about close packed atoms. So they'll start around 50, and as they start to heat over time, they will increase like this. And then as they reach sort of 100%, they'll kind of level out. It will take a longer time to do the last few percents. Right? And the reason it's like this is because the driving force for sintering is a reduction of surface area. So as you have all these tiny little balls in this mold and you heat it up, there's a ton of surface area there. And it will get dense really quickly, but then the surface area decreases quite a bit. So it's going to take a long time for that to go from like 90 to 100% dense. And with that concept, you can think about what would happen if I had small spheres versus large spheres. Which one has a higher driving force? Which one will densify faster? And relate that with the concept that we learned in the intro class about mixing different size atoms. Will that play a role in how dense it starts? Or will it play a role in how fast it densifies? And then we'll also see the effect of time on this process. So if we have, say, intervals of Monday, Tuesday, Wednesday lab that heat them for 5, 10, or 15 minutes, we will expect pellets that have roughly these ranges of the densities, as well as correlating that with small spheres or large spheres or mixed spheres. These may have different profiles, right? So you can imagine that even at identical times, based on the size of the spheres, they may be different densities here. I won't tell you which line is which, that's for the experiment. So let's fill up one of these molds and show you how to do it. We're going to take these spheres and just crimp the plastic, just pour it in here. You're going to overfill it a little bit, right, like with any mold. And we're going to take one of these razor blades and peel off the cardboard coating on it, the cover. And then you're just going to take the edge of this razor blade. You can kind of like tap the mold so that they like settle a little bit. And then you're just going to use that and scrape across. Right? And it's okay to get some on the, it's okay to get on the table. Okay. Now that is the large ones, and then maybe you put the mixed and put the small, and maybe you label it with a pencil and your group number. Okay, now we're gonna have to put a bunch of these in the furnace at the same time, maybe at least 4. And there's a tricky part in that these graphite molds obviously are very slippery and can slide on each other, and also you don't want that to happen when they're inside that tube furnace. So we're going to put a little bit of this carbon tape on it and peel the backing off with this razor blade. And peel this off. And this will ensure that when we put some other molds on top of it, that they stay together. And then I'll show you how we put them into the furnace. So let's just pretend that there's 2 stacked on top of each other now, and we'll go over to this tube furnace. So we're gonna turn on this. We want to make sure that we are flowing argon gas or nitrogen gas into this. So This is argon. We're gonna have two molds stacked on top of each other. We want to take out the lid and this little ceramic insulator block. We're gonna put them right in the end like this. The hot zone in this furnace is like the middle 4 inches or 6 inches or so. You can see this furnace temperature profile, how the middle in inches is about, you know, between the 10 and 16, so maybe 6 inches is like stable temperature. We have a little wire here. We're going to use this to push in the molds. The mold is roughly this size, and we want to push it in so that we have one set of molds here and one set of molds here inside the furnace. So we're going to push the mold until, if we want it centered, then maybe up to here. But if we have 2 sets of molds, then we want to push it until this left dot. I don't know if you can see that one. Then we want to also look and see where the end of this tube is going to match up with our fingers here. So hold your fingers like roughly there. And we're going to use this, and we're going to push in our molds until this wire is flush with the end of the tube. Right? And you'll also notice that this wire has a little hook on it. We can use this after the experiment's done to reach into the tube, hold onto the molds, and pull them back out, because otherwise it's very difficult to get out. Next thing we'll do is we'll put the insulating block in, and we'll see that this cap is actually composed of a few parts. There's a silicone O-ring, a metal ring, another silicone O-ring. These are high temperature silicone. If we go to really high temperature and we don't have that insulating block in, that silicone will degrade also, become very brittle. We take this cap, we put it over 3 holes, put that back ring through. Right, and this is sealing the end. We have 3 washers and 3 nuts, so we're going to put onto this cap and screw it tight. You can pretty much do this hand tight and it will still seal. Just make sure that you go around. One consideration when you tighten this is to hold on to the tube when you tighten it, or else the rotation of the nut will actually also rotate the tube, and you really don't want that after your samples are in, because it's loose powder and it's going to become uneven, right? And you don't want to have to redo all that work. So go around the 3 nuts and tighten them all. Right. We're going to check that this is airtight enough by starting to flow the argon gas. So come around and you see this regulator here. This dial here, we want to start with it counterclockwise until you feel it's like pretty loose. Then you can also seal up this one. This is kind of just a double check. Make sure nothing's just going to flow in there. No big blast of air is going to disrupt our samples. Then turn on the main valve. Slowly, we're going to see the tank pressure on the right side and make sure there's no pressure on the left. Then we're going to gradually screw in this regulator. And we'll see the needle jump a little bit off that. Then we're going to open up this valve. Okay? Here, a little bit of that loop or something here. Make sure that all the connections are tight. Alright, so I can hear gas flowing. This is a visual indicator that gas is coming into this flow meter. We can start to see bubbles coming out of the, there's a tube that comes out on the left side. It goes around and into this water. This serves as 2 functions. One is so we can visually indicate how much gas is passing through and escaping the other side. Also, it is a visual indicator of the flow rate of the gas. We want about a bubble per second going through this furnace to make sure that no oxygen is going to get in there. The other purpose is that the tube is submerged in water so that there can be no backflow of oxygen up into the tube and back into the furnace. If oxygen interacts with this carbon at temperatures above 600 degrees Celsius or so, the carbon will start to turn into CO2, and degrade the molds. That's what we don't want. And you'll actually see these old molds have been affected by that through some experimentation. You see like the surface of them is not very good, and the carbon will come off very easy from them. So you may have to make some new ones of those. All right. The temperature profile for this experiment is going up to 725 degrees C, maybe like 15 or 20 C per minute. So that's going to take 35 or 46 minutes, whatever you choose. Maybe 35 minutes is better. Have it go up in 35 minutes, hold for 5 minutes, 10 minutes, or 15 minutes, and come back down to room temperature as fast as possible. So T3 will be like 5 minutes or so. The whole heat treatment should take somewhere around an hour and a half to 2 hours, and then you should turn off the argon gas after the heat treatment's done, and then you can remove the molds the day after.